any other talk. This is only talk that describes how you start each individual event. Okay. So I give you the instruction first, followed by built-in primary particle generators, and discussion bit about what we call pre-assigned decay. Yes, thank you. That helps me a lot. Okay, introduction. So each event, Geant node doesn't know what you want to do. Of course, it assumes you already defined whatever the geometry. But you have to say, here's my primary event. That means if you are in a collider detector like Atlas, use whatever the physics generators, or PCA or hair weak or whatever, to get all the particles starting from interaction point. Okay? That is a primary. If you have if you have much simpler geometry with just single accelerator, let's say, you may say, here's the beam, so particle comes from here going this way. Or if you are simulating something in the satellite in the space environment, you may define a sphere and say, pick whatever the arbitrary point, shoot particle inward to the satellite. Okay? So they are totally different to each other. That's the reason why we don't have any default. That implies you have to define what you want to do. Okay? So primary particle means particle with which we start an event. Geant4 start the event. Okay? For example, particle made by the PP collision, alpha particle emitted from radioactive material, or gamma ray from a treatment head for the medical use case, or whatever. Okay? Then Geant4 takes care of tracking of these primary particles. That does not necessarily be a single particle. For example, for the case of Atlas, they shoot 300, 400 primary particles per event. And with high luminosity LHC, could be thousands. I don't know how many for Alice. Much bigger, right? So then Geant4 takes care of tracking of these particles in your geometry with physics interactions you define or you pick in your physics list, and generate secondaries doing whatever the physics. And if you define sensitive detectors or scorers, it generated detector response or scores. Okay? Without defining how you start the event, Geant4 cannot do any real physics. Okay? So suppose this blue one is a primary vertex, okay? It has position and time. By default, time is always 0. But you can set time, okay? And with single vertex, you can shoot arbitrary number of particles. They all share the starting point and starting time. Okay? You may have more than one vertices, if you like, per event. And for each vertex, you can define whatever the arbitrary number of particles. That basically allows you to describe your event. Got it? That is the best concept. So G4v user primary generator action is a user mandatory action class. This is the only mandatory action class. All other users classes are initialization classes. But this one is obviously, this is per event, so it has to be thread local. Okay? So please note, this class is to control the generation. I don't say generate event. Control the generation of event. So this class itself does not create primaries, but controlling the creation. Okay? Actual generation should be taken care by G4 primary generator classes. We have many, not many, several, okay? Like a particle gun, the famous one. But all other general particle source, it's yet another famous, and so on and so forth. So the concept is you can utilize these generators and control how you create an event. Okay? Let actual work do by these real generators interfaces. Okay? So G4v user primary generator action. Okay? So this is class is mandatory user class to control the generation of the primaries. Again, let me repeat. This class itself should not generate primaries, but invoke generate primary vertex method of generators that you employ. Okay? So the constructor of this class, you should instantiate primary generator one or more if you need. And it's a good idea to set default values anyway. Okay? Then the second method you really have to implement is generate primary method. This method is invoked at each event, at the beginning of each event. Okay? This constructor is invoked created only once per thread. But this is really the method. It's invoked for every event. Okay? So you may want to randomize the position of the starting point. For example, randomize the vertex position. It often happens. Okay? Even for the case of Atlas, exact I interaction point is different to each event, okay? Depending upon the beam size. Okay? And so on and so forth. So you need to randomize the things. Then set these randomized value to the primary generators. In this case, please do not use UI command. For example, particle gun has a command to set the position. Yes. But don't use UI command because this method is invoked per event. So if you have nice long string manipulations, it breaks the performance. So instead, just invoke the particle gun method, C++ method. You already instantiate generator, so you have a pointer. Okay? Then once you set all the event by event value, randomized values, invoke generate primary vertex method of the primary generators. Okay? So this is a primary generator action. My primary generator action, that is yours. Okay? So in the constructor, in this case, I instantiate particle gun. And please, this argument is quite old, and it should be always 1, please. If you said 2, it just duplicates exactly the same particle twice. Doesn't make any sense. Okay? So please. And you may say, by default, it is gamma. And by default, it should particle toward Z direction. By default, the energy is 100 MeV. And by default, the position of the vertex is 0, minus 50 centimeter. Okay? So these are default. Of course, you can change it by UI command before you start the run. Change the particle if you like, change the position if you like. Okay? Now, here the generate primary method. That is invoked per event. So G4 random direction is a really nice utility method of Geant4. It generates a unit vector randomized in the 4π in a completely uniform way. Okay? So event by event, I just randomize the direction and shoot particle. Okay? So this is the method you invoke, and let the particle gun really do the job of instantiating the primary vertex object and primary particle object. Okay? This is the simplest case, but 80% of use cases, this is okay. You are done. Yes.
For the
Yes, for uniform. Uniform or Gaussian, this kind of simple random number generators are provided. But and you can use some simple math or some cutoff if you like.
Yeah, no.
Yeah.
We already did that.
Yes.
Would like to know if there is something already.
Yes, if you look at the LXR code browser, you should find at least 5, 6, 7 different random number generate method that use exactly the same random number engine, but gives different. In this case, it gives you the three momentum. Okay, so this is a very basic scenario. Then let me continue to built-in particle generators. Okay, we have a few. So primary generator. Okay, this is not your action, but generator. We have particle gun, general particle source. Often it is called GPS, and HEP EVT interface and HEP MC interface. Okay. Let me start with particle gun. This is the simplest one, as we have already seen. Okay. Concrete implementation of the primary generator. But also it's a very good example as a starting point for your specific generator if you need. Okay. It shoots one particle of a certain energy from a certain point at a certain time to a certain direction. That's it. Okay. Various set methods are available. And also UI command are also available for setting initial values or default values if you like. Okay. So one of the really most frequently asked questions is, I want a particle shotgun, or particle machine gun. Can you implement this? I say no, because the concept of splitting the generator and user action is here. You can employ particle gun more than one time in your primary generator action. Okay? And if you change the direction of each particle, that is a shotgun. And if you change the t, starting time of each particle, then that is machine gun, right? So instead of implementing such a fancy weapon, no, okay? In your implementation of the user primary generator action class, you can shoot random numbers in arbitrary directions for shotgun, okay? Or use set method of particle gun to run the change of numbers, okay? And use particle gun as many times as you want within one event, so that you can really shoot many particles at a time, okay? And even change time, change the starting time. Geant4 really respect the time. So if you set 0 to particle number 1, if you set 1 second to particle number 2, in your detector, you really see 2 different times. And also, we really accumulate the propagation time, or even all the secondaries or whatever. So you really see the time counted from the time you specify as a particle gun or a generator in general. Okay? So, and what to do and where to do to implement a fancy weapon. Okay? In the constructor of your user primary generator action, instantiate the particle gun. One object is enough. And it's always a good idea to set some default values, particle type, kinetic energy, position, direction. Okay? Then in your macro file or from your interactive command type, you may type to change whatever the value, if you like. Then in the generate primary method, that is invoked per event. Okay? Okay. Shoot random numbers with arbitrary distribution and prepare track by track or event by event randomized values. Okay? And use set method of the particle gun to set such values. Then invoke primary vertex method of particle gun to get one particle. If you need the second particle within that event, do these steps once again. Okay? Then you have the second particle. Loop it with randomization. You really got machine gun, shotgun, or whatever you want. Okay, that's it. Okay?
They share always the same primary vertex?
No. For each time you create, you invoke this, it generates new primary vertex. It could be the same position, same time, but still having different primary particle. Okay. And that's the reason why you can randomize the position. You can randomize the starting time. Because time and position is an attribute of vertex. Okay. So, example, basic B5 source, B5 primary generator action is a very good example, but don't worry. First of all, this B5 basic example was derived from Slack tutorial. We made it first. We used this hands-on since almost 20 years, polishing it along the time. And then we donated this to the collaboration, so they now use this as a basic example. So you see it today. Okay? So if you see the primary generator action class, that is in the next, you see what I mean. Okay? But this is the generate primaries method. First thing I do is I take uniform random number multiplied by 5. That means it varies from 0 to bit less than 5. Okay? 4.999, whatever. And take integer. That means this I could vary from 0 to 4. 0, 1, 2, 3, 4. And if it is 0, I say it's a positron. If it is 1, I say it's electron, or so on and so forth. So I'm randomizing the particle type here, event by event, or particle by particle. Okay? Then I set this particle type to particle gun. Then I randomize the momentum, okay, and set it, and calculate the kinetic energy. Okay? And this I randomize the direction. Once you set all the randomized values, then I just say, hey, particle gun, it's now time to generate vertex and particle. Okay? And you may repeat these as many times as you like, so that you are really shooting shotgun with a lot of different particle types. Okay? Because particle type itself is also randomized. Okay? Any question for particle gun? I'll come back to this later. Now, interfaces to HEP EVT and HEP MC. This is beneficial only for high energy physics, basically. I'm sorry for that. And each of them are concrete implementation of the primary generator. Okay? Again, that could be a good example. Others, for example, you modify, take this and modify it as they like. Okay? The first one, HEP EVT interface, is suitable to connect to HEP EVT common block. If you don't know what common block is, you are in a good life, yes. But if you unfortunately know what common block is, it's a photon. So basically all the physics generator of physics, high energy physics, used to be written in photon, and they share the same common block to describe the particle primaries. So we have the interface to it, but we hate to link Fortran code with Geant4 C++. So in this case, we just offer the ASCII format in file I/O. Okay. Still, there's an example. Okay. Now, in the modern world, a few generators have already turned into C++. Okay. And they now have HEP MC class that represent primary event. Basically, the same functionality as HEP EVT, but not common block, but C++ class. So now we are happy to connect by executables. So this time we offer both file I/O and also direct linking. Okay, but anyway, they are interface to the physics generators. So if you are a high-energy physicist employing Física, Hairwig, or whatever, this is your option. Okay, then each physics generator, let's say each Hairwig event is taken as one. All the particles are taken associated with one primary vertex, assuming that this is an interaction point. Okay? If you have few interactions per beam crossing, you may invoke HEP-MC interface or whatever more than once with different position. Okay? Also, if you really want, suppose you are an atlas, you really want to see a signal muon, you may, overlapping with minimum bias event. In this case, you may let the Física whatever generate minimum bias event. You read it through the HEP-MC interface, and you may also have a particle gun. That with particle gun, you can shoot signal particle. Okay, you can use more than one generator kind within one event. It's up to you. Just invoke this method of each generator as many times as you need. Okay, and each time you invoke, you may want to change the position and time if needed. Okay, that's the reason why we call it action class rather than generator class. Okay, you now got a clear distinction. Okay, you can employ more than one generators. Okay. Now, general particle source. This one, high energy physicists never use it, I believe. But originally, this was created by ESA, European Space Agency. Actually, guys paid by European Space Agencies to support the simulation of the radiation environment in the space. Okay. The usage, actually, to use it, it's very simple. There's no other way. In your constructor of primary generator action, you instantiate it, and primary generator method, generate primary method. Just invoke this method. That's it. You cannot set anything. There are hundreds of set methods you never understand. I never understand. The only way you can manage is through UI command. It's really, really powerful. But once you start to read the code, you become blind. it's almost like Fortran. The only difference is there is no go-to statement. It's really a nightmare. But it's really powerful. Primary vertex can be randomly chosen from the surface or in the volume of the shape, in particular from the surface. Okay? And the momentum direction, current energy of the particle type can also be randomized. And all these distributions should be defined by UI commands. Okay? And it also has nice event biasing options, okay, by enhancing particle types or distribution of the vertex point or energy or direction, whatever. So, for example, it randomly generates a particle from the side of the, actually, from a plane. So this is the primary vertex position distribution along x and y direction. So it's really starting from a plane, while this is x, z, and y, z. So as you see, it's really a plane. From the plane, it really shoots particles one way or the other. Okay. With this energy spectrum, I don't know what it is, but anyway. The other one, this shoot particles from the surface of the sphere, randomly chosen, with the black body energy distribution. Energy is also randomized. Okay, very nice. Or starting from surface of cylinder with cosmic diffuse energy. I don't know what it is, but someone knows maybe. Or in this case, it still comes from the surface of the sphere. But as you see, there's black belt here. So some tropical region is enhanced. So you can really do this kind of enhancement if you like. Okay? And so on and so forth. There are lots of commands. For example, to specify this kind of energy distribution, what you do is you really set the height of each beam of the histogram. Then general particle source will really randomize the distribution along your histogram. Okay? So it's really, really powerful. But you really have to go through this link to find more than 1,000 UI command, okay? And you have to understand. Okay? To be honest, I've never used it. So here's a comparison. Particle gun versus general particle source. People like general particle source because they misunderstand it's powerful. Yes, it's powerful, but it's dangerous. Okay? So particle gun is simple and naive. Shoot one track at a time. Easy to handle. You really understand what you're doing. Okay? GPS is very powerful, but could be controlled only by the UI command. Okay? Almost impossible to control through the set method. Just forget about it. Okay? Capability of shooting particles from the surface of a volume is really nice. And capability of randomizing the energy, momentum, whatever. Okay? So, if you are basically space application or material science, security kind of things, you may consider using it. If, and only if, you need to shoot primary particles from the surface of a volume, in particular, either inward or outward, GPS is the solution. Okay? If you need a very complicated distribution of the momentum, for example, not Gaussian, but whatever the shape, GPS is the solution because you can always provide histograms. Okay? Otherwise, please use particle gun. You really understand what you are doing. Okay? Because far more than half of the question on shooting primaries always come for general particle source. Okay? It's complicated. Big warning here. Okay? Okay. Now, to close this talk, I mentioned about pre-assigned decay. This is particularly important for ARIS. Okay? And or any nuclear physics simulation, it's also quite important, I believe. And so is the case of Atlas. But anyway, by default, when an unstable particle, let's say pion, comes to its decay point, which Mihari or Dennis had already discussed, it decays, yes. And when it decays, G4 decay process looks at the particle definition class of that particular particle and go to the decay table of that particular type. Okay? For example, pion, it decays to muon and neutrino, yes, to neutrinos, of course. Then shoot random numbers to pick, depending upon the branching ratios, it picks decay channel and use that channel. Okay? But some cases, you may want to really specify, I want to see this particular particle decay this mode, while same particle type but going through this direction. decay that decay mode. You really may want to really specify this decay that, this decay that. Okay? In this case, what we call it a preassigned decay. In this case, once G4 decay process find the track that has already preassigned decay, it does not go look up the decay table, but it exactly follow what you specify. Okay, that's it. Of course, all other physics, for example, Lorentz boost or everything is correct. Just you specify the decay channel. Okay. For example, if you have a fissure whatever creates D0 and D0 decay to germanium whatever, then fissure decays it, right? It knows pure physics. Geant4 does not have full decay table for D0. So you really want to read from HEP-EVT or HEP-MC, the decay chain. And we already have this functionality. Then we exactly follow what fissure ordered. Okay? That is the concept. So you can specify decay channel for each individual particle separately. Here's D0A, D0B. B means number 2. It decays this way, this decay that way. You can specify, even tau or whatever. Okay. So here's a bit of cartoon. Okay. This has to be set at primary particle. Okay. Primary. So for example, this is B minus. I say this particular B minus should decay to D0 mu minus neutrino, and then this D0 should decay to K on mu plus and neutrino. Okay? They all are set at primary particle. And once this is set as a primary vertex and primary particle, Geant4 convert this B minus to G4 track. Okay? Still carrying these information as a dynamic particle. Okay? And when this, and we of course take care of tracking, then once this B meson comes to the decay point, we take them to create secondaries. And this D0 still carries these preassigned decay, so that when D0 comes to this decay point, it decays into these particles. It works that way. So if you have physics generators, just read the physics generators, and Geant4 automatically takes care of it. Okay? That's it. Question?
So, can you go back to slide 15?
Where's the page number? 7. Okay, here it is, yes.
Right. So, if I want to use this histogram with energy and position distribution, so is it a root histogram?
No. I mean, there's a command GPS something and bean. So each bean you have correspond to each single UI command. So if you have 100 beans, you have to have 100 UI commands. Each bean, for each command you define the bean. So it's not a root histogram. No, you have to read root histogram and interpret it and generate UI commands.
Right.
Yeah, it's not that easy.
That's fine.
Or you can do it by yourself. You go on the other side and using the general particle, you are using the simple particle and you implement the visualization, you load your simple particle, and whenever you need to generate
Yeah, we always make big caution when you use GPS. You have to be confident or brave enough. And one thing I forget is that if you shoot particles from the surface, this is not a real kind of, suppose you want to simulate, let's say, a radioactive material, bulk of radioactive material. In this case, alpha starts from somewhere in the middle. Okay? Of course, in the end, it comes out from the surface, yes. But that alpha is already attenuated. Okay? If you shoot particles from the surface, this attenuation is not taken into account. So please be careful. Okay? Okay, I think I'm done.
So we will continue where we finished yesterday, actually, with the physics list. And we go one step deeper, because yesterday in the physics list we used processes. And I mentioned that yesterday I didn't tell too much about the processes, but they are used in the physics list, okay? And today in this lecture, we will see a bit more about the processes and the process concept in Geant4. But not only that, because we have almost 1 hour, so we will talk about the processes in general and the process interface, and we will talk about a very important point, the secondary production threshold. Okay, Makoto mentioned already in the geometry when he was talking about the region that you can set different secondary production threshold. Hopefully after this lecture you will understand what is this secondary production threshold and why you want to set it in a different way in different regions, for example in a complex detector. But let's start with the physics process concept of Geant4. So I already mentioned yesterday, and we will repeat quickly, that Geant4 provides many physics processes already that you can take and use in your physics list. As you could see yesterday, we were seeing some examples. And I also mentioned that processes are kind of building blocks to describe your physics environment. So you can take whatever process you want and you can assign to particles. And how is it possible to use processes to describe any physics processes? The answer is, on the first level, is very simple, because each process, as I mentioned yesterday, will describe a given interaction. Like yesterday we saw, for example, G4 Compton Scattering that describes a Compton Scattering process. Or we saw, I don't know, Coulomb Scattering, or this kind of things. So each process, actually, when I say describes an interaction, means that there must be at least two answers provided by each process. The first one is need to give when the interaction happens. So in other words, when a Compton scattering happens, or in other words, how frequently a Compton scattering happens. And the other answer that the process need to give is that actually what happens with a photon when it participates in a Compton scattering. So we will see that this G4v process interface provides some utilities for each process to give these answers. And we will see what different type of process are possible to implement. But before that, as I mentioned, that Geant4 already provides a huge number of processes. We saw several of them yesterday, and we will just go through quickly again that the process categories, as I mentioned yesterday, electromagnetic, hadronic, decay, special things, transportation, and again a special set of process can be a parameterized process. So we will see tomorrow in more details the electromagnetic category, and you will see that there is the standard electromagnetic category, as I mentioned yesterday. These are providing processes, description of the interactions that can be used from kilo electron volt up to very high energies, but at lower energies they are not very accurate. Okay, these are for applications where they do not care too much about the low energy precision. For application that cares much more of the low energy precision, Geant4 provides this low energy electromagnetic set of processes that will be accurate even at low energies. Okay. And we will see that it's achieved in such a way that there are much more details included in the theoretical description of the interactions. Where much more details very often means, as I write here, including the shell structure of each atom, okay, or including effects like for example mode corrections that are coming from relativistic quantum mechanical description of scattering, for example. Okay, we will see a few things like this tomorrow. And the special category that we will see a bit after lunch is the optical photons that was already mentioned. These are special photons because their wavelength is really high. They are low energy photons. So we cannot really track them like particles. We need to include already some wave-like properties in the interactions. But you will see this after lunch very briefly. Now, other set of processes belongs to the hadronic category. That after tomorrow, Dennis will give three lectures on these processes. You will see much more. You will see tomorrow that there are the photonuclear and the leptonuclear interactions that are interactions of photons and the electrons, for example. So normally they would go to the electromagnetic category, but they are not electromagnetic interactions, so they also belong to the hadronic category. And finally, the special interactions like decay, we will see a bit more, and you will understand what is this decay table that Makoto was talking about after lunch. I will show such decay table, and it will be clear how decay is handled. Then the special process, the transportation process, it's also a process in Geant4 that I mentioned yesterday. Each particle needs to have this process because this is what you can think about as a geometry process. It will always know how far each particle can go till it hits a boundary. Okay. And I mentioned yesterday this set of parameterized processes. You can think about such some fast simulation processes. Now, in the future, in the high energy physics, fast simulation will be even more important than today. So a bigger fraction of the detailed simulation will be replaced by some fast simulation approximation. Okay, some part of the detector, they will just stop doing detailed simulation. They will use some approximation to get some information, for example, energy deposit in a part of the detector, instead of going and really simulating the real energy deposit, to accelerate the simulation, because they won't be able to afford to do detailed simulation anymore. This is why it's mentioned here, okay? But we won't talk about fast simulation actually this week. So let's get back to the process Geant4 process interface, because you could see that from decay till hadronic physics, through electromagnetic down to low energy electromagnetic, no matter which physics process interactions we are talking about, each of them will be a G4v process at the end, because this is the interface that's provided by Geant4 to describe physics interactions. Before we go there, just remind you that Makoto already mentioned that in Geant4, G4 track objects are propagated in a step-by-step way. There is a pre-step point and a post-step point. So something we're limiting the step, so we'll propagate from the pre to the post-step point each track. And we are tracking one track at a time. Okay, we are making one step. If something secondary is produced, we are putting into a stack. And we go till one track, till it dies, goes out of the world, or its energy goes down to zero, or it just disappears. Then we go to the secondary stack and pick up on the top track, and we put and start tracking. And an event finish when we go to the secondary stack and we find it empty. Okay. Then we take another primary and we start the story again. So what is propagated in Geant4 during the simulation? These are tracks, G4 tracks. No, each G4 track, you can divide the G4 track into two parts. Because what is in the G4 track, you can imagine some particles are some particle in the G4 track. But when the particle is already in the tracking, there are two sets of properties of the particle. One set is static. Okay, it do not change at all during the tracking, and actually these properties are exactly the same for all tracks having the same particle type. What I'm talking about is that these static particle properties, for example, charge, mass, and so on, you can imagine, each electron has exactly the same. So these are described in Geant4 in the G4 particle definition objects. So we have an electron, for example. And yesterday I showed that in your physics list, first you define a list of particles, like G4 electron, G4 gamma. And there is one electron. Okay, there is one gamma. Because each of the electrons are exactly the same. These properties are exactly the same. No, there are other properties during the tracking that one given electron during the tracking can be in XYZ position. Okay. Or can have many different energies. But these properties are described in the G4 dynamic particle part of the track. So each track encapsulates these two different objects. One is the static property, and the other one is describing the dynamic properties of the currently propagated particle that will change at each step. For example, the position is changing, the energy might change, and so on. Now, as you can see here, as I mentioned, there are exactly as many particle definitions as you put into your physics list in the construct particle method, as you could see yesterday, the list of particles. But there can be many, even million or more electrons in your simulation with different dynamical properties. For example, different position, different energy, and so on. Now, after mentioning this, as we saw yesterday in the physics list, you take the particle and you will assign some possible interactions, processes to each particle. Now, during the simulation, the list of processes that can happen with a given particle is determined by what you assigned in your physics list. Okay, that's exactly the list. That are the possible interactions for a given particle. So, primarily, this list is determined by the type of the particle, because you assigned in your physics list processes to a particle type. Like, for example, we had the list for electrons, or we had a list of processes assigned to gamma particles. Now, where these processes goes, so each particle has a G4 process manager object, and this is storing this list of the assigned processes. Okay. And each of these processes will be a G4v process, an implementation of this G4v process. So what is this G4v process? This G4v process is the general physics process interface in Geant4. So at each step, as I mentioned, each physics process needs to answer some questions. So the first question is how far the particle goes till the next interaction of that type will happen. Where how far is most often is in space, but in some cases it can be in time. Okay, you will understand later on what I mean. And the second question to answer, as I mentioned, that what happens when the interaction is indeed happening in the post-step point. Okay, what happens when a Compton scattering happens? What happens means that the process needs to be able to answer what happens with the primary particle after the interaction, and if there are any secondary particles, the process needs to be able to produce these secondary particles. So actually, the process needs to be able to transform the primary particle from the pre to the post-interaction state, producing even secondary particles if there are any. So in order to answer these two different questions, the G4v process interface will provide two types of methods. The first one will be something like get physical interaction length. When you implement this method, you need to provide how far the particle goes till the interaction that you are implementing is happening. If it's a Compton scattering, you need to provide something that related to the Compton scattering cross-section, actually, more exactly to the mean free path, so how far the gamma particle goes till the next Compton scattering. And you will get all the information, what is the current material, what is the energy of the photon, and so on and so on. Now, answering the second question, what happens in the interaction, the process interface provides this do-it type of method. This is exactly where you implement what's happening when the given interaction is really happening. Now, there are these two types of methods. But regarding the processes, there can be three different ways in which a process actually can happen, which a physics process can happen. So there are interactions that happening along the step, which means while the particle is moving from the pre to the post-step point, something is continuously happening along the step. Okay. There are some interactions, I will show examples in the next slide for each and it will be clear. There are some others that are happening at the discrete post-step point. Okay, nothing while I'm moving, but when I'm stopping in the next step point, I stopped actually because I'm making an interaction. These are happening at a discrete point. Or a special type of process, set of processes that can happen when the particle is stopped, which means that the kinetic energy goes down to zero. Okay. You will see example for all of this. Now, for each different type, the process needs to be able to tell how far the particle goes till the next, post-step interaction happens, and what happens if the post-step interaction really happening. How far the particle goes till the along step interaction, let it to go, and what happens along this step. Okay. So for each type has one get physical interaction length and one do it method. So in total there can be 6 different methods to be implemented. But of course, not all the interactions has all these 3 possibilities. Some interactions are pure discrete interaction, which can happen at a given point. An example is the Compton scattering, when a photon is scattering on an atomic electron. Okay, it's happening at a given point, the photon goes and interacts with an atomic electron, and this is happening in a discrete point. Okay. So if you want to implement a Compton scattering process, what you need to implement is only 2 methods. You forget the other 2. You implement only the discrete part, the post-step get physical interaction length, and the post-step do it. In the post-step get physical interaction length, you will tell how far the gamma will go till the next Compton scattering, and in the post-step do it method, eventually you will get the track and you need to transform it to the post-interaction state. So actually here, answering the first question, eventually you will use the integrated cross-section of the Compton scattering, while in a post-step do-it method to get what is the energy transfer to the electron and so on, you will use some differential cross-section. Okay, and here the sampling that Dennis was mentioning will arrive and so on. You need to generate a final state. Now, if we go further, there are interactions that are happening only along the step, or happening actually constantly while the particle is moving. This is like the Cherenkov effect when a charged particle is moving in a dielectric medium faster than the light, actually. If you know this, it's a kind of shock wave-like emission of photons. And when the particle is moving, it's constantly emitting photons. So when the particle is moving from the pre to the post-step point, there are many photon emissions along the step. So for these kind of things that happening along the step in a continuous way, what needs to be implemented in the along step get physical interaction length, at how far you let the particle go, okay, and what's happening while the particle is moving, this photon emission that you need to implement in the along step do-it method. Now, the at-rest method, one possible at-rest method is muon minus capture at rest. When the muon goes down with kinetic energy to zero, then what will happen actually, the muon will form a muonic atom, and then eventually it will decay or will be captured, and this muon minus capture will happen as a process. But it's happening when the muon energy goes down to zero, okay? So in this case, at-rest get physical interaction length need to be provided, but if you think that the muon is already at rest, so it doesn't move so far, so actually here the length means time, okay? Because there are two possible interactions for this muon at rest, as I mentioned, either decays or be captured. So there are two competing processes. We will get back to this. And actually, you need to describe these capture interactions. What happens, what are the secondary particles coming from these interactions, since your muon will disappear in this interaction. Now, these are pure atlas, pure continuous, and pure discrete interactions. There are interactions that are both discrete and at rest. This is decay. If a particle can decay, it can decay when it's moving, okay? And it can also decay when its energy goes down to zero. It's there, and after a given time, it will decay. So it can happen either while the particle is still moving or when the particle stops. So in this way, it's a continuous discrete process. So it has discrete and at-rest part, both with the two methods, so 4 methods need to be implemented. No, a very special continuous discrete process, actually 2, is ionization and Bremsstrahlung. I will get back to this at the end of this lecture, because this makes a huge difference in everything. Now, as you could see already yesterday, that in the physics list we assign the processes to a given particle, so there are many possibilities. For example, in case of gamma, we saw that we can assign pair production, Compton scattering, and photoelectric effect. Each of them is a process. And actually, pair production, Compton scattering, and photoelectric is each of them actually a discrete process. It's happening at a given point. But you can think that in case of gamma, there are other possible interactions, like I mentioned, gamma nuclear. So in a complete physics list, you would assign also gamma nuclear interaction for gamma particle. And as we saw, this G4 process manager is storing this list of these processes. And during the tracking, we can always have access to this list of processes. As this process manager can give us the list of the discrete, assigned discrete processes. If we have a particle like a gamma particle, we can always ask the list of the discrete processes, list of the continuous processes, list of the at-rest processes. And during the stepping, each process will be asked roughly what's happening in the pre-step point. Each process will ask that how far I can go till the next pair production is happening, if it's a photon. How far I can go till the next Compton scattering happens. How far I can go till the next photoelectric effect happens. And the shortest distance in a random sampling will be selected, and this will be the process that will happen if the particle eventually, the photon, is really moving to that point. But transportation is also there, assigned to the gamma interaction. So actually, if transportation gives the shortest length, because transportation tells that no, you cannot go till these points, because there is a boundary crossing, that we will stop at the boundary, so nothing happened. Okay. Then we will recalculate in the next step how far we go till the next, pair production, Compton, and photoelectric effect. Why? Because it's a different material than before, so it will change. Okay. So, roughly, this is how the stepping is going. Of course, especially in case of charged particles, this is not as simply as like this. Okay. And what makes the complications? The way in which we describe Coulomb scattering, and this fact that we describe the Bremsstrahlung and ionization as a continuous discrete interactions. And the fact that we describe the Bremsstrahlung and ionization as continuous discrete interaction, this is exactly the introduction of secondary particle production threshold. So here we stop with the processes in general and stepping. And tomorrow afternoon, in the third electromagnetic lecture, we will go a bit deeper into this stepping and the effect of multiple scattering and so on to the stepping. And now we will go and we will try to understand what is the secondary particle production threshold. Okay, so any question regarding what I was talking about so far? Yes? Of course, it's randomly selected, because what the process provides actually the mean free pass. This is a mean quantity. And how the mean free pass comes, you will understand tomorrow afternoon. So it's interesting because, as in physics, it's not that first the mean free pass was decided, then it was calculated. But based on some statistical consideration, there was a quantity that was actually meaning the mean distance between some interactions. And the mean free pass is related to the macroscopic cross-section that is related to the atomic cross-section. Okay, but we will see tomorrow. If no question, then let's move to the production threshold. So, we will talk about Bremsstrahlung and ionization. I will show this in the first two slides, I think, in case of Bremsstrahlung. Then I will make the connection to ionization. So let's have a look to the Bremsstrahlung. So what is Bremsstrahlung? That a charged particle in the field of an atomic electron, in the field of the atom, or also in the atomic electron, but it's much smaller contribution to the differential cross-section, emits a photon, a Bremsstrahlung photon. Okay. Now, if we see the differential cross-section for Bremsstrahlung photon emission for a 1 GeV electron in silicon, and we plot it, then we will get this blue curve. Now, what is it? Actually, it will tell the differential cross-section is differential in emitted photon energy. So this distribution, if you want, it will tell the rate of emitting a photon that the primary was 1 GeV with 400 MeV. This is the rate. And you can see if we go down with the photon energy, so this electron will emit photons with lower energy with a higher rate. If I enlarge this part, you can see here that the lower the photon energy, the higher the emission rate. Which means that if a 1 GeV electron moves in a silicon material filled with silicon atoms, then then more likely it will emit lower and lower energy photons. Now, at the same time, if you see that this is the photon energy in different materials, but this curve is the important because it tells you how far the photon goes if in silicon and other materials starting with a given energy. So you can see the low energy photon doesn't go so far. Higher the energy, go further and further. Of course, because this will be some kind of absorption length. The higher the photon, the further it will go. But the important thing is that the electron would emit more likely low energy photons. That anyway doesn't go far because they will be absorbed. The lower the energy, they will absorb quicker. So they don't go so far. So let's suppose that you have a detector and you want to collect energy deposit. Then your detector collecting energy deposit from a given part has some resolution in space. Okay. Now, if we want to draw something like this, I would say that this is your detector, and there are these 4 cells, and each of them has some dimension. Now, when an electron is moving through this detector, then we can see that it can emit Bremsstrahlung photons. But what will happen is that it will emit a Bremsstrahlung photon, but it doesn't go far. It will be absorbed immediately here, or will be absorbed here, or will be absorbed here, will be absorbed there. So how far this energy goes that these low energy photons are taking away from the electron? Actually, they don't go anywhere if we consider that this is your resolution. As long as all the energy stays inside this, your detector cannot make a difference whether that energy was taken away for a short length from the primary particle by the photon and put a bit further. The difference would be seen by your detector only if the electron would emit a higher energy photon that goes significantly further, and for example here it would go to the other side, to the other pixel, and it would deposit that energy that it was taken away from the primary here. Okay, so what we can say is that as long as we have a detector that has a spatial resolution that it's significantly worse than small energy photons can travel, then if I generate all these small energy photons along the track and I'm tracking them and I deposit the energy where they went, okay, where they absorbed at the end, or I do not generate them at all, but where they were created, I say that that given energy is deposited there immediately at the trajectory point. And I do not generate these photons, I'm not tracking. From your detector point of view is exactly the same. Doesn't see the difference. It's just because the spatial resolution is much worse than these photons are going in length. However, high energy photons that can go further than your spatial resolution of your detector need to be generated because that would make a difference. If you would not generate them, and you would assume that that energy that they're taking away from the primary particle is deposited exactly where the primary particle was going, you would do a mistake. Because in the reality, they would go to another cell of your detector. Okay. Is it clear? Okay. So, this is exactly why we introduce a secondary photon production threshold in case of Bremsstrahlung. Why? First of all, the computationally most expensive things that you can do is to generate a particle, create a new track, especially for nothing, because it doesn't go more than one step. Okay. You just lose lots of time for nothing. Because you created a particle with 2 kilo electron volt in lead that even you don't see how far it goes. And you lost lots of time. Second, you stop with your primary here and again and again and again and again. So instead of making one long step, you make many, many small steps while you were stopping just to generate a photon that doesn't go anywhere. So, and how many photons you need to generate? The rate is going up like this. So you will see that plenty of photons with very low energies, even down to very low energies. So what we do in high energy physics or even in intermediate energies, this kind of simulation where we generate all these photons for nothing, it's not feasible. It's simply impossible. If the electron energy is high like 1 GeV, forget it. So what we do is that we introduce a secondary gamma production threshold, as you can see here. And what we say, what we say is that we do not generate photons, secondary photons, in Bremsstrahlung photon emission that would have an initial energy smaller than this energy threshold. Okay. For this, we don't stop, we don't generate them. Instead, what we do, we just move and we will generate only photons that has secondary photons that has higher energy than this energy threshold. So what we do, we move from the pre to the post-step point with this electron. Now the post-step point, there will be either Bremsstrahlung photon emission, but then the photon energy will be higher. Higher means high enough to go through another part of your detector. But below, we do not stop, so we make a long step. But when we reach to the post-step point, we know that, okay, we did not generate many, many, many low energy photons. So actually, the electron energy in the post-step point need to be lowered because some energy was actually deposited. Okay. We did not generate the photons, but actually those energy were already taken. And we describe this energy loss along the step, while the particle is moving from pre to the post-step point. We describe the energy loss due to this sub-threshold photon emission with the mean value called stopping power. Okay? And this is actually the mean value between 0 and threshold, the mean energy loss value in unit length. Mean value, okay. And it's called, strictly speaking, it's called restricted stopping power because it's restricted to this range of integration. The full stopping power that you heard about already is the same integral having the upper limit being the energy of the primary electron. Okay. Now, what does it mean for the higher energy part? That we generate these photons as in discrete interaction, so we'll stop and generate photons in Bremsstrahlung emission with energy higher than the secondary gamma production threshold. So we will have a cross-section for this interaction, which is the integral from the threshold up to the primary electron energy. Okay. So actually we remove from the full cross-section that part that would result in very low energy photon emission. And we account it as a long step continuous energy loss with a mean value. Is it clear? Okay. Now I was talking about Bremsstrahlung photon emission, and you saw this bad behavior of the differential cross-section. I could tell almost the same things if I would say ionization, okay, which means that an electron not emitting photon, but generating a secondary electron, kicking out in a way on an atomic electron. It would be exactly the same. If you would see what is the differential cross-section of transferring energy to the secondary electron, you would see a very big peak at very low energies, which means that most likely the secondary electron in an ionization will take away very, very small energy from the primary. And these electrons doesn't go practically anywhere because in one step they will deposit all their energy and they stop. So it's the same story like with the low energy photons. The only difference is that when we are talking about ionization, in case of Bremsstrahlung, the secondary particle is a gamma particle. In case of ionization, these are electrons. So we are talking about secondary electron production threshold, not secondary gamma production threshold. But the same things, it will mean a limit in the integral. And when we are talking about absorption length of the secondary photons, in case of ionization, it translates to the range of the secondary electron. Now, this is a concept using secondary electron production threshold that's must be used actually, in intermediate and high energy particle transport simulation. It's not really a question. And it's used by other simulation toolkits as well. So whatever was listed yesterday, you saw, I don't know, Fluka, Penelope, MCMP, GSNRC, whatever. Everybody is using the same thing. This is called condensed history simulation. Because actually the low energy part we describe in a condensed way. Now there is, however, a difference between all those simulation toolkit and Geant4 regarding the secondary production threshold. It is that you can, as you can see, when you define a secondary production threshold, in case of Bremsstrahlung secondary gamma particle production threshold, it will enter into the model level, in the description level, as a limit, as an energy limit in the integral. So finally, eventually, it's used by the model as an energy. But when you need to decide what is the proper value for this threshold, what are those photons that you don't care, because it doesn't change anything in your case, it will depend on your spatial resolution, which means length. Okay. And if you would give it in energy, that would be cool, because we use it in energy, okay, in the model. But then what would happen if you say that you don't want to generate photons below 20 kiloelectron volt? If it's lead, the material, it's a different length. So if this is length, if this is lead, and this is argon gas, then it's not the same, because a photon with 20 kiloelectron volt, it will go much less in lead than in argon gas. So when you need to decide what would be the proper length, depending on your detector spatial resolution with different materials, then you think in length. Okay. So, because no matter if you say an energy, I can translate it into length. Because if you say an energy, an electron energy, secondary electron energy, or secondary photon energy, it will be a length in absorption length. Or if you say an absorption length, I can get back what is the proper energy. So what is the photon energy that has that absorption length? Okay, so the translation is always possible. But you as a user, when you want to decide what's the proper value, then it will depend on length. What is your size of your detector? So this is why Geant4 provides this possibility that you need to give this production threshold in length. While other simulation toolkits will ask you to give it in length, in energy, but then you need to compute that, okay, you have the same size, but this is lead, this is argon, so the energy here that you would like to see is different because it's higher, because you can go the same length in lead. with a higher energy photon compared to organs. So it becomes really, really complicated because you need to think in advance a lot. While giving in length is easier because this is exactly what you see, what you think immediately. It's much more intuitive. So in Geant4, you give the secondary production threshold in length. It has a default value 1 millimeter. In case of some predefined physics lists, it's already 0.7. And you could see yesterday this interface method in the physics list, the set cut method. You can use it to set production threshold in your physics list. Or you can use user interface commands that yesterday you were already trying, like /run, /beamon, whatever. You can set cut value to any value through your user interface. And you can also specify for one particle, because it will set 0.1 millimeter secondary production threshold for electrons and for gammas as well. But if you want to set different for electron and different for gamma, you can use this user interface command that you can do easily set this for different particles. And this length will automatically translated by Geant4 at initialization to a given energy that we will use in each model in Bremsstrahlung and ionization. We will use as an integration limit to produce the cross-section, the restricted cross-section and the stopping power tables and so on. Now, when you set a very low value, Geant4 will actually print a table. What is the production threshold and actually in length and in energy at the beginning of the simulation. And sometimes you will see that you can set 10 to minus 10, and it won't be 0, but will be 990 electron volt. Because when we translate to energy, there is a minimum limit. This minimum is coming because of some theoretical approximations actually in the ionization model that we are using behind the skin. Now, there are some other models for ionization that does not have this limit. So actually you can safely lower this value with the user command. Okay, you can set it to very low, like 100 electron volt. But when you set it to 100 electron volt and you are using the EM standard models, for example, and you are running the simulation and it goes through, it doesn't mean that you did some meaningful things. Just the fact that it does not crash or it doesn't mean that it's meaningful. Unfortunately, it's more complex. So what particle has secondary production cuts? They are secondary particles. We saw that gamma production threshold. Gamma has secondary production threshold. It's used in case of Bremsstrahlung. Electron has secondary electron production threshold. That's used in case of ionization. Positron, that can be used in case of pair production. Protons, they are different because they are used not in this way, like I described as an integral limit. And it's used as a limit. Actually, the length will be transformed to energy, and it will be used as a recoil limit. Okay, maybe Dennis will talk about it Thursday. These secondary production thresholds for gamma and electron production are applied in Bremsstrahlung and ionization. However, there are other interactions, gamma interactions, that are producing secondary electrons. Compton scattering. When a gamma goes through a Compton scattering, it's producing secondary electron. Or photoelectric effect, when a photon is absorbed by the atom, and there is a photoelectron emitted by the atom. So the secondary particles are electrons. There is a possibility to apply this energy limit also for those interactions. By default, it's not applied because the concept is different. Okay, there is no limit in integration. It's not the same. We know that we don't generate electrons in ionization below 222 kiloelectron volt. I just said something. Now, why do we generate secondary electrons below 222 kiloelectron volt in Compton scattering? So you can use this apply cut command not to generate in case of photons, photon interactions as well. it can give you some good percentage of speed up, actually. Now, as I mentioned, this way of describing ionization and Bremsstrahlung is necessary. It's not necessary. Practically, you could set the secondary production threshold to 0 if you are using, in case of Bremsstrahlung models, yes. In case of ionization, if you are using a proper model, proper theoretical description, that will be fine to produce even low energy secondary electrons. Then you can set it to 0. Then it means that everything you described as discrete interaction, because you will stop here with the electron producing this photon, that move here producing this photon, no matter how low is the energy. It's possible. The problem is that it's not feasible. Okay, you will spend so much time with this, creating this low energy secondary electrons in ionization, photons in case of Bremsstrahlung, and you will stop so many times with your primary electron that you could not do simulations. You should wait 100 years now for a simulation. So in high energy physics, we need to use it. Tomorrow I will talk about, in the second electromagnetic lecture, about the DNA physics. They don't have any secondary production cuts, but they are working at lower energies. They describe each photon emission. Okay, they describe each electron emission. But it has the price that it's terribly slow. Now, as an example, what happens if we set a proper or not an appropriate or a not appropriate secondary production threshold? So imagine the following simulation, that you have a 45 MeV electron coming from this direction, hitting a silicon target that has 5 micron thickness. And what you are doing in your simulation, actually, you simulate the mean energy deposit. So you will hit many times. You will repeat with many primary particles, which means that you write a high number to run a beam on. And at the end, you calculate what's the mean energy deposited in this thin silicon, 5 micron silicon, by these electrons. And you do it in such a way that you start with a very small production threshold, 1 micron, then 2, 5, 10, and so on and so on. You increase the secondary production threshold. So what will happen? You will generate secondary gamma and secondary electrons. If you set it to 1 micron, you will generate always all the secondary photons and secondary electrons that would go further than 1 micron. If you set it to 2 micron, that you would generate all the secondary photons and electrons that go further than 2 micron. But you do not generate secondary photons and electrons that would not go further than 2 micron. You assume that energy was deposited along the primary electron track. And as you can see, if you are moving from 1 micron till 5 micron, that the mean energy does not change at all, which means that it's totally unimportant whether this energy, here the electron comes, emits 1 photon that has 1 micron or 2 micron length. It comes 2 micron here, it will deposit that energy here instead of here. Okay. Nothing happens, everything is stable. Now you reach the 5 micron, and above 5 micron, what does it mean, 10 micron? That you don't generate photons that do not go further than 10 micron, and you assume that energy was deposited by the primary particle along this trajectory. But if you would generate a photon that goes to 9 micron here, that you don't do if it's 10 micron, then it could go away from your target. And instead of depositing the energy in your target, would take away that from your target. So you start to do mistakes. And bigger mistakes you do if you don't generate more and more photons that would go away from your target. So what is the proper secondary gamma electron production threshold in this case is determined your target size. Okay, you generate everything that potentially goes away in a big fraction, okay? And you don't generate secondaries that will anyway stay there, because from your simulation there is no difference. In other words, if you have a detector that's a huge crystal, that you can afford to have a very high cut, okay? Because most of the secondaries will stay in your detector crystal. But if you have a fine, very granular structure, you need to use a low production cut, because you want to generate all the secondaries that can go to another cell. Okay? So this is what you can do with the production threshold, and you can horribly optimize your simulation, and the simulation time will change drastically. Okay, if you are setting a proper production cut in that region of your detector that you are interested in, because production threshold comes into a region, as Makoto mentioned. Other regions where you are not interested, or you have big crystals, or just a big block of concrete, then you set whatever, 10 kilometers, you don't care. But in a sampling calorimeter, you will set a very low value. And your simulation time will be determined by that part, because you generate much more particles. But be careful, because it's easy to make mistake and get wrong result. So just a few things at the very end that I was actually already mentioning, that I was trying to say each time during the past 1 hour, secondary production threshold. But we will never say this. Everybody is saying that production cut, because it's a cut in secondary production. So when you see in the manual or examples or whatever that cut, or the command run / set cut, it refers to production threshold, but we are using this cut expression. Okay. And these things that I already actually mentioned, for completeness, they are also in the slide. So that's it for the general process interface for today. And from tomorrow, with the electromagnetic physics, actually, we will see how the process is built up in the electromagnetic from models, and what kind of processes and models are available. On Thursday, you will see the same in the hadronic part, how a hadronic process is built up to answer all those questions that we were talking about today. And after lunch, there will be a short lecture just to mention a few topics that are not really strongly belong to electromagnetic or hadronic, like a bit decay and optical photons as well, and so on. Is there any question? Yes? Yeah. Yeah. Yeah, but you mean that here I emit photons and here I don't emit photons? There is I didn't go into these details, but there is a command to do this. Even if I set, because if you go closer and closer to boundary, that you want to emit photons to lower and lower energies, okay, because it can go. And there is a command to do this, actually. By default, it's not there because of many reasons, but it's possible. That will give you the full correct behavior. But as you can see from this example, here it doesn't change too much. If 5 micron is still fine, gives a proper result. Nothing? Okay. Yes. Yes. Yeah. No, not this charge. This charge is a static charge. So this you cannot update. It belongs to the particle. No matter what happens, it's the same. What you could do, you could create other particle. Yes. Yes. What I would do, I don't know if Dennis has another things. I have never done these things, but I could implement a process for this, and I would generate a particle like changing the particle, you know. I would define particles for this. Yeah. You cannot update the static in the particle definition. Okay, this is you don't change, because just imagine if you would change, static means that there is only one object. So if you would change the charge for one electron, that you would change for all the electrons, not only for that one. But as Makoto mentioned, that it well can be that there are dynamic charge and dynamic mass for sure properties in the dynamic particle. Its initialized might be based on the static things, but that you can change. The mass for sure.
Yeah, so
the mass.
you have a process that will accumulate charge as a stripped ion goes through the material.
Yeah.
But that's part of the process code, not part of the particle.
Yes. Do you mean that you implement a process and the process will change this kind of things? As an interaction. Because this is the part of the process that I mentioned, that the process needs to answer the question, what happens if the interaction happens? So you transform the pre-interaction state to the post-interaction state. In your case, it will change the dynamic charge. I think lunchtime.